All right, today we're going to talk about internal resistance having to do with batteries. It's not a topic in your AP1. I know you did some circuits already and everything. We use batteries to do some work. But there is another thing that does pop up with batteries. Is sometimes it pops up in the AP, and it may or may not this year since it's a shortened version. But you have to have an idea of what internal resistance it is, because sources of EMF always have an internal resistance. Being internal, it's on the inside, is kind of hard to measure. It gets a little bit tricky. So that's what today's about, is how to find internal resistance, especially if you're using a battery for a circuit, which is pretty common. So you can click on the inside the batteries and look at the site and look at the energy, how the battery works and everything. You got an anode and you got a cathode and a chemical in the middle. And when you hook up to a circuit, it starts a chemical reaction. It pumps charges from one to the other and so on. But it's a source of EMF called electromotive force. Okay? So EMF is short for electromotive force. It's a voltage. It's a source of potential is what it is. Voltage is how you measure that stuff. But EMF is what you're measuring with a voltmeter when it's not hooked to a circuit, when there's zero load whatsoever. So when there's no load, there's no current flowing anywhere, the potential you're measuring actually is technically electromotive force. Okay? Now what the difference between that is and your terminal voltage, that's in a second here. So voltage is what you measure when you put your terminal, you across the terminals of a battery. You put your wire across on the voltmeter. You're measuring the terminal voltage, but technically we're going to use the terminal voltage term when you actually have a circuit hooked up. We don't have a circuit hooked up here. So anytime you try to put across the A and the B, you're going to measure what's called the EMF, which is like measuring right across your battery without any internal resistance whatsoever. So we're going to make this whole thing your battery, and this represents not an external resistance, but an internal resistance, like the goo between your anode and your cathode. So it kind of represents the goo between your anode and your cathode, which you can't really draw very easily on the inside of there. Okay, so this is your battery, or your voltaic cell, I should say, inside here between the A and the B. Now, if you were to put a voltmeter across the A and the B, this being the positive side over here, you're actually measuring the EMF. Sure, it's across the terminals, but there actually isn't any current flowing. Because what happens, a voltmeter has a very high resistance, such a high resistance that you don't get a flow of current through the voltmeter. So you really haven't caused any current to move. You're measuring the electric pressure on one side compared to the electric pressure on the other side, and that voltage difference is really called the electromotive force, or the EMF of the what we would call a battery or a voltaic cell. Okay, and we use EMF, the epsilon. It's not permittivity of free space with electrostatics. We use this symbol a lot and a lot of others. It actually stands for the EMF. Okay, or what the potential is when a battery is not hooked to anything else. Okay, so as soon as you connect a voltmeter, there's not really much of any current that flows. It's almost pretty much zero that flows through. You're measuring the electric pressure on one side compared to the other. Very, very little flows whatsoever. So technically, you're still measuring the EMF of the thing. So to measure, so when you hook this up across the A and the B without a source of current flowing through the battery, you're actually measuring the EMF. Okay, so you can't measure the EMF when you're hooked to a circuit, because when the current flows, well, there's an issue that happens, which we'll look at here in a second. So we're modeling this battery with an internal resistance. We're going to use a small r. Big R is going to be an external resistance, so we hook across the A and the B externally over here. Okay, so the battery, or voltaic cell, is inside the green box there. Alrighty, so when talking about Kirchhoff's rule of summing up the voltage drops, so whatever plus you get, boost you get from the battery, you're going to lose that in your circuit somewhere. So this is an example of basically of finding what your terminal voltage is. This would be the voltage when you're hooked up across the circuit, when your current's actually flowing through an external resistance. We don't really use this for the battery because technically when we've hooked up, there isn't any current flowing. But we're going to use something like that in a moment here. So that's when current flows through the battery. There is an internal resistance or a voltage drop across there. And so what the terminal voltage is, it's that EMF when nothing's hooked up to when you do hook it up, you get that little loss there what the actual terminal voltage is. But this is going to make a little more sense in a second here, because we don't usually use it in that function exactly like that. Similar, because we're going to call this an I times R here in a second, which is what is going to make a little more sense, I think. So there's your model, there's our battery, there's our A and the B. We've got a resistor. Now we need, that's the internal resistance. So here's, we'll get that in a moment. So if you want to find out what the terminal voltage is, you just find the difference between your potential, which actually, if you're not hooked to a source, you're actually just measuring your EMF technically. Okay? So remember also there's EMF, not just have internal resistance. All right, let's get further into that. So we're going to hook this up in a moment to a circuit and talk about how we're measuring our terminal voltage versus your EMF. So in circuits, you got current going in one direction from the, we're talking about positive current flow from the positive terminal to the negative terminal. So a battery would increase the potential, okay? Something like a resistor would decrease the potential as you got across the thing, okay? But we're treating a battery as an internal resistance. So we're going to have a little bit of a drop from the E when you hook it to a circuit. So here we go. We got an external circuit set up here. We've got a 1 ohm resistor. It's not very big, but we have an internal resistance over here. So if we do our loop rule, going from the positive to negative, we got a loop of current go from over here. So whatever plus we have from the battery is going to be the same minus over here, because everything's going to sum up to 0. So in this case, we already measured a 9-volt battery to be 9 volts. But as soon as we hook up a 1 ohm resistor, it drops clear down to 3 volts. So you think that's a high resistance or a low internal resistance? We'll find out in a second. So to find out what the internal resistance is, there's some measurements we have to make. Okay? So first of all, no voltmeter. So because the voltmeter draws, well, technically no current, it's very little current. They are in a series with both of these R's. So if they're both in a series, you have the same current going through this resistor, the internal one, as you do the external one. So using Kirchhoff's law of summing up the potentials, you get a plus voltage from the EMF when you're not hooked up. This, you get a drop in your voltage from the internal resistance of the battery, then another drop from the external resistance over here. And those two have to be add up to be the same as this. Now, so some of you might be thinking, hey, so there's a 3-volt terminal voltage across here and here. So that means there's 3 volts across a 1 ohm resistor. If you take 3 divided by 1, that means there's 3 amps flowing through this. And since it's a series, I have 3 amps going through there. I also have 3 amps going through there. So I actually know the current running through the whole system. I know that this is my 9. That was measured when it wasn't hooked up. I just found that that has to be a 3 because my terminal voltage when hooked up is 3 volts across the A and the B. That's the same as across this right over here. So I, using Ohm's law, I equals V over R. So now if we have 3 volts divided by 1 ohm, that is clearly 3 amps going through not just the battery, but also going through this external one. But here's the other thing. This I times R, that's just your 3 times your 1. That's 3 volts. So really all you have to do is solve for that little R. That's how you find the internal resistance of a battery. First you measure what the EMF is, you measure what the voltage is when it's hooked up to a circuit, and you use that difference to find what the current flow is. And once you've calculated the current flow, you can just solve for what that little R is, or the internal resistance of your battery. So plugging numbers in, 9 goes in for that because that's the EMF. This is actually 3 volts because that's what they said the terminal voltage is, which is actually the IR right here. It's one and the same. That's a 3. So now we have a 9 minus a 3, so we're a 6 minus this. So it's a 6 minus the I. And remember the I we already said was 3. So 6 minus 3R, you solve for the R, you get 2 ohms. So there's a lot of stuff that's going to make it look more complicated than that here in a second. So remember the terminal voltage is the IR. That's the drop right here. This is the voltage drop right here, I times R. And since I already know that to be 3, and I know the resistance is 1, that makes that 3. I know there's 3 amps going through there. But that's still a 3 volt here. But that means that's 3 amps over there. There's only one unknown I have over there. So it looks a little more complicated when we do this because they're trying to solve and break everything down. So yes, that is the same as the IR, and I is the V, and we know that's a 3, and we know that's a 1, so we know now that that's a 3. So there's not a question that that's a 3 and a 3, or that's a 3. So 9 divided by, but so long story short, you can do something that looks fancy like this and more complicated, but you're going to find out the internal resistance, like we said earlier, was just 2 ohms. Okay, from that. So it seems a little large for a 9-volt battery to have a 2 ohm resistance, but as they tend to age, sometimes that resistance changes a little bit. Oh, by the way, good experiment to do here. I don't know how much time we have. I can't really see the time. Hopefully I have time. Proof example, not a good idea. Says if you only have, so we already found it's a 3 amp current going through there. So why is it maybe a bad idea to do the whole, I don't know, 1 ohm thing across a 9-volt battery? Here's a 9-volt battery. Here's, I don't know if it's 1 ohm or not, but it's steel wool. I don't know if you can see that. There's little sparks going on. Let me get that close to the camera. I don't want to burn up my keyboard. Let me make it a little fluffier there. Steel wool all over the place. Am I high enough? There I am. So what happens is this stuff catches on fire. It's still oxidized. Now that we got it hot, it's oxidizing by itself in the air. And the steel wool is actually on fire. It's got a low resistance. That means a lot of current flows through there and it get things rather hot. And I got to get off the wooden porch. All right, we're on fire here. All right. Vaya con Dios.